Okay, we are having this problem of interval scheduling. In interval scheduling, we are given jobs, and each job has some starting time and some finishing time. So, what does greedy algorithm suggests? It suggests that just sort the intervals in the increasing order of their finishing times. That means we have these intervals sorted in the increasing order of their finishing times. That means finishing time of I1 is less than equal to finishing time of I2 and so on. So what is the algorithm? The algorithm is simple. We maintain a variable which stores information about the finishing time of the last interval selected. So initially, suppose we make the counter r, or we can just make it simply x, and we can initialize it with 0. And we run a loop through our intervals I1 up to in, and each iteration we check if the starting time of the interval is greater than this x value, we can update x as the finishing time of the interval. So in this case, x becomes the finishing time of I1. So in the next iteration, we check if the starting time of I2 is greater than the finishing time of I1. That means I2 is compatible with I1. If not, we check the next interval, and so on. And suppose in the ith iteration, we check the starting time of IR. If it is greater than X, then we can update X equal to the finishing time of IR. And this is how we keep on selecting intervals if it is compatible with the last interval selected. So the greedy solution provides us a solution S which consists of number of schedules, right? And suppose the number of schedules that the greedy solution is written as is equal to k, and the optimal solution O has the number of intervals n. So what we are supposed to prove that k is equal to n, as we can have different number of optimal solutions, but the number of intervals in each solution should be same. So our job is to prove that the k is equal to n. So initially the greedy solution was S and the optimal solution is O, and these are the jobs I1, I2, I3 up to IK. All these jobs are sorted either on the basis starting time or finishing time. Both the order gonna be the same. Similarly, optimal solutions, optimal jobs are also sorted in the increasing order of finishing times or starting times. Both the order going to be the same. And we assume that k is less than equal to n. K is less than n, and we prove by contradiction that it is not possible. K is actually equal to n. So we will be using this claim, and we will be proving this claim later. It says that any job IR in the greedy solution is the finishing time of the IR is less than equal to the finishing time of GR. IR belongs to greedy solution S, and GR belongs to optimal solution. Now what we are supposed to prove is according to the greedy solution, IK is the last job which is selected, and we have an assumption that k is less than n. But we know that since we are using this claim which says that finishing time of IK is less than equal to finishing time of JK, this is a claim. And we also know that JK and JK plus 1 are compatible because they both are in optimal solution. So the finishing time of JK is less than equal to JK plus 1. Since JK and JK plus 1 are compatible. From these equations, we can conclude that finishing time of IK is less than equal to the starting time of JK plus 1, which implies that ik and jk plus 1 are compatible. That means ik is not the last job. That means we are having the option of jk plus 1 after we have selected ik, which is a contradiction because our greedy solution says ik is the last job selected. But since we have proved that it is not possible, we are having the option of jk plus 1, and jk plus 1 comes after ik in the sorted order when we are having intervals in increasing order of their finishing times. So it is clearly not possible, which means that k is equal to m. Now we will prove our claim, which says that the finishing time of any interval ir is less than or equal to finishing time of jr for all r where the r can take any value from 1 to k, where k is the cardinality or the number of intervals in the greedy solution. So we will use proof by mathematical induction. For r is equal to 1, it is very trivial. That means finishing time of I1 is less than or equal to finishing time of J1. Since we know that we have already sorted the intervals in the increasing order of finishing times, I1 is having the least finishing time. So this statement is always true. So our next step, the assumption, the hypothesis is going to be, we assume that finishing time of IR is less than or equal to J of R. Now we have to prove the induction step, which says that I of R plus 1 is less than or equal to J of R plus 1. We'll use contradiction to prove this step. We say that suppose it is not true, that means f of gr plus 1 is less than f of ir plus 1. Now, let this way, these are the intervals which is sorted in the increasing order, their finishing times. I1, I2, up to IK1, up to IK2, and so on as IK3, right? And we see that IR, this IK plus 1 is equal to IR. That means this is the RH job in the greedy solution. And IK2 is the R plus 1 job in the optimal solution. And IK3 is the R plus 1th job in the greedy solution, right? So we prove this. We know that J of R and JR plus 1 are compatible jobs. So from this, we can write this expression that the finishing time of JR is less than or equal to starting time of JR plus 1, since JR and JR plus 1 are compatible to each other. And since this is our induction hypothesis that the finishing time of IR is less than or equal to J of R, so we can always use this. From these two statements, we can say that IR and JR plus 1 are also compatible to each other, right? And we had an assumption that JFR plus 1 is less than f of IR plus 1. So since the way our algorithm works, it always selects an interval which is the first compatible one, right? So after IR, right? After IR, in the sorted order, we have an option of JR plus 1. So our algorithm, so if we see this sorted order, after we have selected IR, we are having the option of JR plus 1. So our algorithm should have picked JR plus 1 instead of IR plus 1. But in our algorithm, as you see that after IR, we have selected IR plus 1, but it should not be the case. The algorithm should have picked GR plus 1, which is a contradiction. And hence, we can say that f of IR plus 1 is less than equal to f of JR plus 1.